Hello and welcome. Tonight we're going to explore something that sounds like science fiction, but will reveal one of the most beautiful truths about our existence. Imagine this. You're standing outside on a clear night looking up at that bright dot in the sky. Jupiter, the largest planet in our solar system, our cosmic guardian. Now imagine, it simply vanishes. Not gradually, not peacefully, but in an explosion so violent it would rewrite the rules of our entire solar system. What would happen to Earth? What would happen to us? The answer is more terrifying and more wonderful than you might think. If you're curious about the hidden forces that protect our fragile world, stay with me through this journey. And if you enjoy these deep dives into cosmic mysteries, like and subscribe really help us continue exploring the universe together. Now, let's begin. To understand what we would lose if Jupiter exploded, we first need to understand what Jupiter actually is. And I promise you, it's far stranger and more important than most of us ever learned in school. Let's travel back 4.5 billion years. Our solar system is young, chaotic, a swirling disk of gas and dust, orbiting a newborn star. In this cosmic storm, something extraordinary begins to happen about 500 million miles from the Sun. Material starts to accumulate, not just rocks and ice like the inner planets, but something far more ambitious: hydrogen, helium, the very elements that make up stars themselves. Jupiter forms quickly, violently, like a cosmic vacuum cleaner switched on at maximum power. Within just a few million years, a blink of an eye in cosmic terms, it grows to 3 to 18 times the mass of Earth. To put that in perspective, if Earth were a marble, Jupiter would be a basketball. But that comparison doesn't even begin to capture the truth. Jupiter contains more mass than all the other planets, moons, asteroids, and comets in our solar system combined, and still has room to spare. Here's where it gets fascinating. Jupiter almost became a star. If it had gathered just 80 times more mass, the pressure and temperature at its core would have triggered nuclear fusion. We would be living in a binary star system. Our night sky would never truly be dark. But Jupiter stopped just short of that threshold, becoming what astronomers call a failed star, or more poetically, a sub-brown dwarf. Now you might wonder, why does this matter? Why should we care about this massive ball of gas floating out there in the darkness? On January 7, 1610, an Italian mathematician named Galileo Galilei pointed a primitive telescope at Jupiter. What he saw changed humanity forever. 4 points of light moving in orbit around the planet, moons. For the first time, humans witnessed celestial bodies orbiting something other than Earth. It was proof that Earth was not the center of everything. We were just one world among many, but Galileo saw something else that night, something he couldn't have fully understood. He was looking at a system, a family, a cosmic structure that would later prove essential to Earth's survival. Those 4 moons, Io, Europa, Ganymede, and Callisto, are each worlds unto themselves. Europa hides an ocean beneath its icy crust that contains twice as much water as all of Earth's oceans combined. Io is the most volcanically active body in the entire solar system, with hundreds of volcanoes constantly erupting. Ganymede is larger than the planet Mercury, and Callisto is so heavily cratered, it looks like the universe used it for target practice. These moons exist because Jupiter exists. They orbit Jupiter because its gravitational pull is so immense, it holds them in place despite the sun's competing influence. And this is where we begin to glimpse Jupiter's true role in our solar system. Fast forward to July 16, 1994. Astronomers around the world aimed their telescopes at Jupiter waiting. They were about to witness something that had never been observed before in human history. A comet called Shoemaker-Levy 9 had broken apart into 21 fragments, and those fragments were about to slam into Jupiter at 134,000 miles per hour. Over the course of 6 days, those impacts created fireballs larger than Earth itself. One impact released energy equivalent to 6 million megatons of TNT, That's 600 times the entire nuclear arsenal of Earth at the height of the Cold War. The scars in Jupiter's atmosphere were visible for months afterward. Here's what scientists realized as they watched that comet didn't hit Earth. It hit Jupiter instead. And this wasn't a coincidence. This was Jupiter doing what it has done for billions of years, protecting us. You see, Jupiter's massive gravitational field doesn't just hold its moons in orbit. It acts as a cosmic shield for the inner solar system. Comets and asteroids that come screaming in from the outer reaches of our solar system often encounter Jupiter first. And when they do, one of three things happens. Jupiter's gravity deflects them away, entirely sending them back into the dark. Or Jupiter captures them, pulling them into orbit or into collision. Or, in rarer cases, Jupiter slingshots them away at even higher speeds, flinging them out of our solar system entirely. Think about what this means. For 4.5 billion years, while life was slowly, painstakingly evolving on Earth, from single cells to fish to dinosaurs to us, Jupiter has been out there silently intercepting threats we never even knew existed. Astronomers call this the vacuum cleaner theory, though that name doesn't quite capture the majesty of it. A more accurate description might be Jupiter is our guardian giant, our cosmic bodyguard, standing watch in the darkness. And here's something that will change how you see the night sky forever. Without Jupiter, Earth would be hit by asteroids and comets between 1,000 and 10,000 times more frequently than we are now. Let that sink in. The asteroid that killed the dinosaurs 66 million years ago, that catastrophic impact that reset life on Earth. Events like that would happen not once every 100 million years, but potentially once every 100,000 years, perhaps even more often. Human civilization is only about 10,000 years old. Agriculture cities writing everything we call history has occurred in just the last tiny sliver of time. Without Jupiter's protection, it's entirely possible we would never have had the stable, safe environment necessary for civilization to develop at all. Now, here's the beautiful irony: Jupiter can't actually explode. Not in any natural way. Planets don't explode like stars do. Jupiter doesn't have the mass to trigger fusion, so it can't go supernova. It doesn't have the internal pressure to blow itself apart. It's actually remarkably stable and has been for billions of years. But tonight we're going to imagine the impossible. We're going to ask, what if some cosmic catastrophe beyond the laws of physics as we understand them? What if something caused Jupiter to explode? What if 318? Earth masses of hydrogen and helium suddenly released all their energy in one catastrophic instant. What would happen to its moons? What would happen to Saturn, Uranus, Neptune? What would happen to the asteroid belt, that carefully balanced ring of rocks between Mars and Jupiter? And most importantly, what would happen here on our small, fragile world, 500 million miles away? The answer will take us on a journey through time, from the first millisecond of destruction to the first hour, the first day, the first year, and beyond. We'll watch as the catastrophe ripples outward through space, traveling at speeds that would make light itself jealous. We'll see worlds die. We'll see orbits shatter. We'll see a solar system transformed into something unrecognizable. And by the end, you'll understand something profound, that every time you look up and see that bright dot in the night sky, you're looking at the reason we're here at all. You're looking at the difference between a world where humans gaze up at the stars and a world where nothing gazes at anything because nothing complex enough to gaze has survived. But before we can understand what we would lose, we need to understand what happens in that first terrible moment. Because the explosion itself would be unlike anything our solar system has ever witnessed. An event so powerful, so violent, that it would make supernovas seem almost gentle by comparison. Let's find out what happens when 318 Earth masses decide to stop being a planet. The moment has arrived. Jupiter, our guardian giant for 4.5 billion years, is about to experience something that defies every law of planetary physics. Let's imagine the trigger, some cosmic force beyond our understanding, activates. and in 1 millisecond, everything changes forever. What I'm about to describe to you isn't just dramatic. It's based on real physics, real energy calculations, and real data we've gathered from decades of studying Jupiter. The numbers are almost too large for human minds to grasp, but we're going to try anyway. Picture Jupiter as it exists right now, 88,846 miles in diameter. That's so large you could fit 1, 3, and 21 Earths inside it with room to spare. Its mass is 1.898 x 10^27 kilograms. Those numbers are abstract, so let me give you something concrete. If you tried to drive around Jupiter's equator at highway speed, it would take you 6 months of non-stop driving. Light itself traveling at 186,000 miles per second takes 7 seconds to cross from one side of Jupiter to the other. Now, let's talk about what Jupiter is made of. This is crucial to understanding the explosion. Jupiter is approximately 90% hydrogen and 10% helium, with trace amounts of methane, ammonia, water vapor, and other compounds. In other words, Jupiter is essentially the same composition as the Sun. It's just not quite massive enough to ignite. It's a star that never quite made it, a giant ball of fuel with no spark, until now. When our impossible explosion begins, we need to understand the energy involved. Every nuclear weapon ever built by humanity, every bomb from Hiroshima to the largest hydrogen bomb ever tested, the Soviet Tsar Bomba, all of them combined equal about 6,000 megatons of TNT. That sounds like a lot. It's enough to destroy human civilization several times over. The energy required to completely destroy Jupiter would be approximately 1 billion times greater than that. Not 1,000 times, not 1 million times. 1 billion times the entire nuclear arsenal of humanity at its peak. Let me put this another way. The energy released would be equivalent to the Sun's entire energy output for nearly 100,000 years, compressed into a single moment. It would be like watching 100,000 years of sunlight happen in the blink of an eye. The explosion begins at Jupiter's core, deep within, where pressures reach 100 million times Earth's atmospheric pressure, and temperatures soar to 43,000 degrees Fahrenheit. Higher than the surface of the Sun. Something triggers. The core, which contains most of Jupiter's heavy elements compressed into a region about the size of Earth, suddenly releases its binding energy. In the first millisecond, the core temperature spikes to levels we normally only see in stellar explosions. The hydrogen surrounding the core, remember, hydrogen is the most explosive element in the universe, begins to undergo rapid fusion. Not the controlled, steady fusion of a star, but catastrophic runaway fusion, a hydrogen bomb the size of a planet. Within 1/10 of a second, the shockwave from the core reaches Jupiter's outer atmosphere. Jupiter's famous bands, those beautiful stripes of rust cream and burnt orange that we have photographed from Earth, simply cease to exist. The Great Red Spot, a storm system larger than Earth that has raged for at least 350 years, longer than the United States has existed as a nation, vanishes like smoke. Here's something that gives me chills every time I think about it. We know from the Voyager missions in 1979 and the more recent Juno mission that Jupiter's winds reach speeds of 400 miles per hour. Those are the fastest winds in the solar system. But in this explosion, material is moving outward at 10% the speed of light. That's 67 million miles per hour. At that speed, you could travel from Earth to the Moon in 13 seconds. By the 1-second mark, Jupiter no longer exists as a coherent object. What was once a planet is now an expanding sphere of superheated plasma radiation and debris. The sphere is already larger than Jupiter was just 1 second ago, and it's growing exponentially. Now, let's talk about the radiation. This is where things get truly horrifying from a physics standpoint. Jupiter's explosion would release what astronomers call a gamma-ray burst on a planetary scale. Gamma rays are the most energetic form of light in the universe. They're what's left over from the Big Bang, what pours out of black holes, what bathes the cores of nuclear reactors. A single gamma-ray photon carries more energy than 1,000,000 visible light photons. The gamma-ray pulse from Jupiter's explosion would light up every detector on Earth. Astronauts aboard the International Space Station would need to immediately take shelter in the most shielded section of the station. Our satellites, our GPS systems, our communications infrastructure, everything in orbit would be bombarded with radiation at levels they were never designed to handle. But here's the thing that might surprise you. Earth's atmosphere would protect us, just like it protects us every day from cosmic rays and solar radiation. The gamma rays would be absorbed in the upper atmosphere, creating spectacular auroras visible from pole to equator. The sky would light up with colors most people have never seen. Deep purples, electric greens, crimson reds swirling across the heavens. It would be beautiful. Terrifying, but beautiful. However, and this is important, the immediate radiation wouldn't kill us. We're too far away. 500 million miles is a vast distance even for gamma rays. The inverse square law of radiation would save us from the initial pulse, but that's only the beginning of our problems. Within the first minute, something else starts to happen. Jupiter's magnetic field, which is 20,000 times stronger than Earth's, suddenly collapses. This field extends millions of miles into space, trapping high-energy particles and radiation belts, similar to, but far more intense than Earth's Van Allen belts. When the field collapses, those particles are released all at once. A wall of energetic protons and electrons, accelerated to near-light speed, begins expanding outward. This is cosmic radiation on a scale our solar system has never experienced. And it's heading in every direction at once. The Juno spacecraft, which has been orbiting Jupiter since 2016, giving us unprecedented data about the planet's interior atmosphere and magnetic field. Juno would cease to exist in the first microsecond. Every piece of data it collected, every photograph it took, every measurement it made would be vaporized before it could send a final transmission. In fact, let's talk about what we learned from Juno, because it makes this scenario even more real. In 2018, Juno's instruments detected that Jupiter's magnetic field is even more complex than we thought. It's not uniform. It has patches of reversed polarity like a magnet with multiple north and south poles randomly distributed across its surface. The energy stored in that field is equivalent to several quintillion kilowatt hours. When it collapses, all that energy has to go somewhere. Some of it converts to heat, adding to the explosion's fury. Some of it accelerates the charged particles I mentioned, and some of it creates electromagnetic pulses, EMPs, that will eventually reach Earth. By the 5-minute mark, the expanding debris cloud has grown to encompass the orbits of all 4 Galilean moons. But we'll talk about their fate in a moment because their story deserves its own telling. At 10 minutes, something remarkable and terrifying happens. The debris cloud becomes visible from Earth, not with telescopes, with the naked eye. Jupiter, which normally appears as a bright, steady point of light, suddenly blooms into a fuzzy growing spot. Observers in dark locations away from city lights would be able to see structure in the expanding cloud. It would look like a flower opening in time lapse, except this flower is made of superheated gas expanding at millions of miles per hour. Astronomers around the world would be simultaneously excited and horrified. Every telescope would turn toward Jupiter. Every detector would be recording. Social media would explode with speculation. What's happening? Is it a comet impact like Shoemaker-Levy 9? Is it something else? Within an hour, the truth would become apparent through spectroscopic analysis. The light from the explosion would show the signature of hydrogen fusion. Not just chemical reactions, not just a collision, fusion. Stellar processes occurring where a planet used to be. And scientists would realize Jupiter hasn't just been hit by something. Jupiter itself is undergoing catastrophic disintegration. Let me give you a comparison to help you visualize the scale. The Chicxulub impact, the asteroid that killed the dinosaurs, released energy equivalent to all 100 million megatons of TNT. It excavated a crater 93 miles wide and threw enough debris into the atmosphere to block out the sun for years, triggering a mass extinction. Jupiter's explosion would be 10 billion times more powerful, not 10 times, not 100 times, 10 billion times. If the Chicxulub impact was a firecracker, Jupiter's explosion would be every volcano on Earth, erupting simultaneously combined with every earthquake, every hurricane, every atomic bomb, all happening at once. And then multiply that by another million. There's simply nothing in human experience to compare it to. The closest analogy might be supernova explosions we've observed in distant galaxies. But those are stars, not planets. Jupiter would be the first planetary explosion ever witnessed in cosmic history. At least the first one we know about. By the end of the first hour, the physics of the explosion would be settling into a new equilibrium. The initial fireball would begin to cool, though cool is relative. We're talking about temperatures dropping from millions of degrees to merely tens of thousands. The expansion would continue, but the rate of acceleration would slow as the energy dispersed across an ever-growing volume of space. What's left is no longer a planet. It's a nebula, a cloud of gas and dust where Jupiter used to be. Over the coming hours and days, that cloud would continue expanding, growing larger than Jupiter's original orbit, eventually stretching across millions of miles of space. But the explosion itself, that initial catastrophic release of energy, would be complete. The sound and fury would give way to an eerie, spreading silence as the debris dispersed into the vacuum. And in that silence, 4 small worlds that have orbited Jupiter for billions of years would face their final moments. Io, Europa, Ganymede, and Callisto, the Galilean moons that changed our understanding of the cosmos, about to experience something no moon has ever survived. 4 worlds, each one a masterpiece of cosmic architecture, each one a potential harbor for life, each one with mysteries we've only begun to unravel. In one terrible hour, they will all be gone, and the universe will lose something irreplaceable. Let me tell you about these moons, because understanding what we're about to lose makes this story far more profound than just an exercise in physics. Io orbits closest to Jupiter, just 262,000 miles from its surface. That might sound like a lot, but it's actually closer than our moon is to Earth. And that proximity has transformed Io into the most geologically violent place in the entire solar system. When Voyager 1 flew past Io in March 1979, navigation engineer Linda Morabito was examining images of the moon's edge, trying to determine its exact position for trajectory calculations. She noticed something strange, a plume extending 190 miles above Io's surface. At first, she thought it was another moon hiding behind Io. Then she realized the truth. She was looking at a volcanic eruption in progress, an eruption so massive it was visible from space. We now know Io has over 400 active volcanoes. Some of them erupt continuously. Others blast sulfur and sulfur dioxide 250 miles into space. The moon's surface is constantly being renewed, buried under new lava flows. There isn't a single impact crater on Io, because volcanic activity erases them faster than they can form. If you stood on Io's surface, which would be a terrible idea for many reasons, you would see the ground itself flowing like water fountains of molten rock arcing overhead, and the massive face of Jupiter filling half the sky. Why is Io so volcanic? The answer is tidal heating. Jupiter's enormous gravity stretches and squeezes Io as it orbits the same way you can heat up a ball of clay, by kneading it repeatedly. This generates enough internal heat to keep Io's interior molten. Europa and Ganymede's gravitational tugs add to this effect, creating a perfect storm of tidal forces. The heat flux from Io's surface is 2.5 watts per square meter on average, That doesn't sound like much until you remember Io is the size of our moon. The total heat output is about 100 terawatts, roughly equal to all of human civilization's power consumption. A moon generating as much heat as all of humanity's power plants combined. Now, imagine what happens when Jupiter explodes. In the first second, Io is bathed in radiation intense enough to vaporize rock. But Io doesn't even have time to melt. The shockwave traveling faster than Io's escape velocity of 1.6 miles per second simply tears the moon apart at the molecular level. One moment, Io exists. The next moment, there is no Io. Just the expanding cloud of sulfur, iron, silicon, and oxygen atoms where a moon used to be. All those volcanoes, all that geological activity that took 4.5 billion years to build, gone in less time than it takes to blink. Europa is next. And Europa's destruction might be the greatest tragedy of all. Europa orbits Jupiter at 417,000 miles, about 1.6 times farther out than Io. From Earth, Europa looks like a cracked eggshell with reddish-brown lines crisscrossing a bright, icy surface. Those lines are actually cracks in ice that can be 12 miles deep. And beneath that ice, water, liquid water, an ocean of it. In 1996, the Galileo spacecraft's magnetometer detected something extraordinary. Europa has an induced magnetic field. This only happens when a conducting fluid, like salty water, moves through Jupiter's magnetic field. The data suggested an ocean beneath the ice, and every subsequent measurement has confirmed it. Europa's ocean is estimated to be 40 to 100 miles deep. To put that in perspective, Earth's deepest ocean trench, the Mariana Trench, is only 7 miles deep. Europa's ocean may contain twice as much water as all of Earth's oceans combined. And it's kept liquid by the same tidal heating that makes Io volcanic, though in Europa's case, the effect is more gentle. Here's what makes this profound. Wherever we find liquid water on Earth, we find life. Deep ocean vents, Antarctic ice lakes, even miles underground in solid rock. If there's water, there's life. Europa has liquid water. It has energy from tidal heating. It has organic molecules delivered by comet impacts. It has everything necessary for life. We've been planning missions to Europa for decades. NASA's Europa Clipper, scheduled to launch in 2024, will study the moon's ice shell and subsurface ocean. The European Space Agency's JUICE mission will also study Europa. We've been slowly, carefully working toward answering one of the most profound questions in science. Are we alone in the solar system? Europa might hold the answer. Beneath that ice and that dark ocean, there might be ecosystems we can barely imagine. Not intelligent life, probably, but life nonetheless. Microorganisms adapted to total darkness, feeding on chemicals from hydrothermal vents completely independent of the sun. Or maybe something more complex. Europa's ocean has existed for billions of years. Life on Earth went from single cells to complex organisms in that time frame. What might have evolved in Europa's endless dark ocean, we'll never know. When Jupiter explodes, Europa is approximately 13 light minutes away from the explosion's center. The radiation arrives first. 13 minutes after the explosion begins traveling at the speed of light. Europa's thin oxygen atmosphere, created by radiation breaking apart water molecules on the surface, is stripped away instantly. Then, the thermal pulse arrives. The ice begins to sublimate, turning directly from solid to vapor without becoming liquid first. Imagine the entire surface of a moon, the size of our moon, boiling away into space. That's what happens to Europa. The shockwave hits minutes later. By this point, Europa's ice shell is already compromised, fracturing and exploding outward. When the shockwave arrives, traveling at millions of miles per hour, it doesn't just crack Europa. It pulverizes it. And here's the heartbreaking part. For a brief moment, Europa's ocean is exposed to space. That hidden ocean we've spent decades trying to reach, that ocean that might harbor life, suddenly has no protective ice shell above it. The water begins to boil in the vacuum, flash freezing into ice crystals even as it evaporates. If there is life in that ocean, microbes clinging to hydrothermal vents, complex organisms swimming in the dark, they experience something no life form should experience. Their entire world, from surface to seafloor, is torn apart and scattered into space. Within an hour of Jupiter's explosion, Europa's ocean, billions of cubic miles of water that existed for 4.5 billion years, is dispersed into a cloud of ice crystals and water vapor, stretching across millions of miles. The ocean that might have answered the question, "Are we alone?" is gone before we could ever sample it. Ganymede faces a similar fate, though its story is different. Ganymede is the largest moon in the entire solar system, larger than the planet Mercury. It's the only moon known to have its own magnetic field generated by a liquid iron core just like Earth. It also likely has a subsurface ocean, sandwiched between layers of ice in a structure scientists call an ice sandwich. Ganymede orbits 665,000 miles from Jupiter. It has a surface covered in two types of terrain: dark, ancient, heavily cratered regions, and bright, younger groove terrain that suggests recent geological activity. The groove terrain is particularly fascinating. It shows evidence of tectonic activity, meaning Ganymede's surface has been reworked by internal forces. When Juno flew past Ganymede in June 2021, it provided the first close-up images in over 20 years. The data showed that Ganymede's magnetic field is even more complex than expected, with multiple poles and field lines that interact with Jupiter's magnetosphere in intricate ways. That magnetic field, which has protected Ganymede for billions of years, collapses when Jupiter explodes. The moon is left defenseless against the onslaught of radiation and debris. Being farther from Jupiter gives Ganymede slightly more time, perhaps 20 minutes before the worst effects arrive. But time is not salvation. It's just a longer wait for the inevitable. The thermal pulse melts and vaporizes the surface ice. The shockwave tears through the groove terrain, erasing geological features that took millions of years to form. Ganymede's internal ocean, if any life exists, there meets the same fate as Europa's. And Ganymede's magnetic field, that unique characteristic that made it special among moons, ceases to exist, along with the moon itself. Callisto, the outermost Galilean moon, orbits at 1.17 million miles from Jupiter. It's the most heavily cratered object in the solar system, a record of 4.5 billion years of impacts preserved in ice. Callisto's surface is ancient, largely unchanged since the solar system's early days. Looking at Callisto is like looking at a photograph of what the early solar system was like. Callisto also likely has a subsurface ocean detected through magnetic field measurements. But Callisto is different from Europa and Ganymede. It shows no signs of recent geological activity. Its surface is dead frozen, a museum of ancient history. That distance from Jupiter, nearly 3 times farther than Io, gives Callisto about 40 minutes before the full force of the explosion reaches it. If Callisto had scientists living on it, they would have time to observe what happened to the inner moons, time to record data, time to send farewell messages, time to understand exactly what was coming for them. But time would not be enough to escape. The debris cloud expanding from Jupiter's explosion would be moving faster than any spacecraft we've ever built. Faster than the Voyager probes, faster than New Horizons, faster than anything human technology has achieved. When the debris hits Callisto, it hits with the force of countless nuclear weapons. The ancient cratered surface, that geological record spanning billions of years, is obliterated in minutes. Callisto, the last witness to the early solar system, is destroyed. Within 1 hour of Jupiter's explosion, all 4 Galilean moons are gone. 4 worlds, each unique, each scientifically priceless, each potentially harboring life or evidence of how life begins. Reduced to scattered atoms in the expanding debris cloud, And they're not alone. Jupiter has at least 80 known moons. Most are small, irregular chunks of rock and ice captured by Jupiter's gravity at various points in the solar system's history. Each one has its own orbital characteristics, its own composition, its own story. When Jupiter explodes, they all share the same fate. Think about what this means. In that first hour, we lose not just one world, but an entire system of worlds. We lose Io's volcanoes, Europa's ocean, Ganymede's magnetic field, Callisto's ancient surface. We lose dozens of smaller moons we've barely studied. We lose the natural laboratory where we were beginning to understand how moons form, how tidal heating works, how life might exist in unexpected places. The Galilean moons have been objects of study and wonder since 1610. 4 centuries of observation, decades of spacecraft missions, countless hours of analysis. All of it becomes historical record in an instant. No more mysteries to uncover. No more surprises waiting to be discovered. Just data from the past and an expanding cloud of debris where a moon system used to be. But as profound as this loss is, as tragic as the destruction of these worlds might be, the consequences are only beginning. Because that expanding debris field, that cloud of gas and rock and ice moving at millions of miles per hour, is heading somewhere. It's heading outward into the asteroid belt and beyond, carrying with it enough kinetic energy to reshape the entire outer solar system. Between Mars and Jupiter lies a region of space that looks empty at first glance, but contains millions of rocky bodies, ranging from tiny pebbles to mountain-sized asteroids. This is the asteroid belt, and for 4.5 billion years, it has existed in a delicate gravitational dance choreographed by one dominant partner, Jupiter. When that partner suddenly vanishes, the dance becomes chaos. The asteroid belt isn't quite what most people imagine. Movies often show spacecraft dodging asteroids every few seconds, weaving through a dense field of tumbling rocks. The reality is far more subtle and far more interesting. If you were standing on an asteroid in the belt, you likely wouldn't be able to see another asteroid with your naked eye. The average distance between asteroids is about 600,000 miles, more than twice the distance from Earth to the Moon. Yet, despite this apparent emptiness, the belt contains between 1.1 and 1.9 million asteroids larger than half a mile in diameter. Add in all the smaller rocks, and we're talking about trillions of objects. The total mass is estimated at about 3% of the Moon's mass. Not much compared to planets, but spread across a ring, 140 million miles wide, it represents a substantial amount of material. Here's what makes the asteroid belt fascinating from a gravitational perspective. It shouldn't exist at all. In the early solar system, this region should have coalesced into a planet. There was enough material here in the right place at the right time. So, why didn't it? The answer, once again, is Jupiter. When Jupiter formed, its massive gravity stirred up the asteroid belt region, increasing collision velocities. Instead of gently sticking together to form larger bodies, asteroids started smashing into each other with enough force to fragment. Over millions of years, Jupiter's gravitational influence prevented planet formation and actually reduced the belt's total mass through ejections and collisions. What we see today is the leftover debris from a planet that never was held in check by Jupiter's gravity. The key word there is held. Jupiter doesn't just prevent asteroids from forming a planet, it keeps them in stable, predictable orbits. In 1867, American astronomer Daniel Kirkwood noticed something peculiar. When he plotted the distribution of asteroid orbits, he found gaps. Regions where almost no asteroids existed. These gaps corresponded to orbital periods that were simple fractions of Jupiter's orbital period, 1, 2, 1, 3, 2, 5, and so on. We now call these the Kirkwood gaps. And they're one of the most elegant demonstrations of orbital resonance in nature. An asteroid in a 1-3 resonance orbits the Sun 3 times for every 1 orbit Jupiter makes. This means it encounters Jupiter at the same point in its orbit repeatedly. and the repeated gravitational tugs add up over time, eventually ejecting the asteroid from that orbital distance. It's like pushing a child on a swing. One push doesn't do much, but if you push at the same point in the swing cycle every time, the effect accumulates. Eventually, the child is swinging very high. In the asteroid belt, swinging very high means getting ejected into a completely different orbit. This delicate balance has existed for billions of years. Asteroids drift slowly through the belt, occasionally colliding, sometimes being nudged by Mars's much weaker gravity, but always held in check by Jupiter's overwhelming gravitational dominance. The belt is stable because Jupiter is there, massive and predictable, maintaining order through sheer gravitational force. Now, imagine Jupiter explodes. In the span of one day, everything changes. The first effect is immediate. Jupiter's gravity simply stops. For the inner asteroid belt, roughly 250 million miles from where Jupiter was, the change in gravitational force is noticeable within about 35 minutes, the time it takes for gravitational changes to propagate at the speed of light. Yes, gravity travels at light speed according to Einstein's general relativity. When a massive object suddenly disappears, the gravitational information of its absence spreads outward at 186,000 miles per second. But here's the thing, asteroids don't suddenly fly apart. They're still orbiting the Sun, and the Sun's gravity is far stronger at their distance than Jupiter's was. What changes is the fine-tuning, the subtle gravitational nudges that kept everything stable. Think of it like removing one leg from a three-legged stool. The stool doesn't immediately fly apart, but it's no longer stable. Any small disturbance will tip it over. Within the first day, the Kirkwood gaps begin to fill. Asteroids that were in unstable resonant orbits, previously ejected by Jupiter's repeated gravitational tugs, suddenly find themselves in orbits that are no longer unstable. They're not being shepherded anymore. They drift inward or outward depending on their specific orbital characteristics. The Trojan asteroids face a more dramatic fate. These are two groups of asteroids that share Jupiter's orbit, clustered around the L4 and L5 Lagrange points. Stable gravitational pockets located 60 degrees ahead of and behind Jupiter in its orbit. There are over 7,000 known Trojan asteroids, though the actual number is likely much higher. The L4 and L5 points exist because of a beautiful mathematical quirk. In 1772, Joseph Louis Lagrange discovered that when you have two massive bodies orbiting each other, like the Sun and Jupiter, there are 5 points where the gravitational forces and orbital motion balance perfectly. 3 of these points, L1, L2, L3, are unstable, like balancing a pencil on its tip. But L4 and L5 are stable like a marble settling in a bowl. The Trojan asteroids have been sitting in these gravitational bowls for billions of years. Some of them are substantial. 624. Hector is 250 miles long, larger than many moons. These aren't tiny pebbles. They're mountains floating in space, held in place by Jupiter's gravity. When Jupiter explodes, the bowls disappear. The Trojans suddenly find themselves in solar orbit, but with the wrong velocity for their current position. They're moving at the speed they need to stay in Jupiter's orbit, but Jupiter's orbit no longer has a massive planet creating gravitational structure. Over the course of days and weeks, the Trojan asteroids begin to disperse. Some drift outward towards Saturn's orbit. Others fall inward toward the asteroid belt, and potentially toward the inner solar system. 7,000 asteroids, some of them huge, suddenly freed from their gravitational prison and wandering into new orbital paths. This is where things get genuinely dangerous for Earth, though the danger unfolds over years and centuries rather than days. Let me introduce you to a concept called orbital perturbation. When an asteroid's orbit changes even slightly, the effects compound over time. An asteroid whose orbit is altered by just 1% might not seem dangerous initially, but over hundreds of orbits, that 1% change can move the asteroid from a safe trajectory to one that crosses Earth's path. We've seen this happen on a small scale. Asteroid 99942 Apophis, discovered in 2004, will pass extremely close to Earth in 2029, closer than our geostationary satellites. That close approach will alter Apophis's orbit, and for years, scientists calculated whether it might hit Earth on a subsequent pass in 2036. Fortunately, better observations ruled that out, but it demonstrated how orbital mechanics work. One close approach changes everything. Now, multiply that by thousands of asteroids, the former Trojans drifting inward, asteroids from the Kirkwood gaps moving into new orbits, the entire belt stirred up by the gravitational ripples of Jupiter's disappearance, and then add the debris from Jupiter itself. Trillions of tons of material, some of it moving fast enough to enter the inner solar system within weeks. Within the first week after Jupiter's explosion, astronomers on Earth would begin detecting orbital changes. Asteroids that were in predictable cataloged orbits would show discrepancies. Objects would appear in unexpected positions. And slowly, the horrifying truth would become clear. The stable asteroid belt configuration that has protected Earth for billions of years is breaking down. Here's a specific example that illustrates the danger. There's a group of asteroids called the Hildas, about 4,000 of them in a 3-2 resonance with Jupiter. They orbit the Sun 3 times for every 2 orbits Jupiter makes. This resonance keeps them in a stable triangular pattern that never brings them too close to Jupiter. When Jupiter explodes, the Hildas lose their resonance. Their orbits become unpredictable. Some will be pushed outward by interactions with other asteroids. Others will fall inward. A percentage of them, we can't know exactly how many without complex simulations, will eventually end up in Earth-crossing orbits. The Hildas aren't particularly large asteroids. Most are between 9 and 60 miles in diameter. But that's more than enough to cause a civilization-ending impact. The asteroid that killed the dinosaurs was only about 6 miles wide. A 30-mile Hilda asteroid hitting Earth would release energy equivalent to several billion nuclear weapons. It would be an extinction event that would make the dinosaur extinction look minor. And it wouldn't be just one asteroid. Over centuries, dozens or hundreds of formerly stable asteroids would find themselves on collision courses with Earth. The statistical probability of impacts would increase dramatically. Some studies estimate the impact rate could increase by a factor of 100 or even 1,000. Let me put that in concrete terms. Currently, Earth is hit by asteroids large enough to cause regional destruction about once every 1,000 years. Civilization-ending impacts happen roughly once every 100 million years. If Jupiter's explosion increases impact rates by a factor of 1,000, regional destruction events would happen every year. Civilization-ending impacts would occur every 100,000 years. Human civilization is about 10,000 years old. In a post-Jupiter world, we wouldn't have survived long enough to build cities, let alone develop technology. But the asteroid belt's chaos doesn't just threaten Earth. It threatens every inner planet. Venus and Mercury would also face increased bombardment. Mars, being closer to the asteroid belt, would have it even worse than Earth. And here's something that would fascinate astronomers even as it terrified them. For the first time in 4.5 billion years, the asteroid belt would have a chance to form a planet. Without Jupiter's gravity stirring things up, increasing collision velocities, asteroids could begin to gently accumulate again. Given 1 billion years, a new small planet might form in the belt. But that's cold comfort for anyone living in the inner solar system over the next few 100,000 years. The transition period, as the belt reorganizes itself into a new stable configuration, would be catastrophic for life on Earth. By 1 week after Jupiter's explosion, the immediate effects on the asteroid belt would be clear. Orbital tracking stations would be overwhelmed with new data. Previously stable orbits would show concerning changes. The Trojan asteroids would be visibly dispersing, and scientists would begin the grim work of calculating which asteroids now pose threats to Earth. The calculations would take months, even with supercomputers. There are too many variables, too many asteroids, too many possible interactions. But preliminary results would suggest a terrifying conclusion. Earth's protective bubble maintained by Jupiter for billions of years had burst. We were now exposed to the full fury of the solar system's remaining debris. Yet, even as the inner solar system faced this new bombardment threat, another drama would be unfolding farther out. Because Jupiter wasn't the only giant planet in our solar system. Saturn, Uranus, and Neptune still remained. And they were about to discover that the solar system they had known for billions of years had fundamentally changed. Saturn sits in its orbit, 890 million miles from the Sun, majestic and serene with its spectacular ring system. For 4.5 billion years, it has shared the outer solar system with Jupiter, the two gas giants locked in a gravitational relationship that has shaped the architecture of our entire planetary system. In 1 month, Saturn will discover what it means to be alone. The outer planets, Saturn, Uranus, and Neptune, exist in a realm of space most people never think about. It's cold out there, unimaginably cold. At Saturn's distance, the Sun appears 100 times dimmer than it does from Earth. It's still the brightest object in the sky, but it's a point of light rather than a disk. The warmth and energy that make Earth habitable are distant memories in the outer solar system. Yet, these worlds are far from dead. They're dynamic, complex, and in their own way beautiful. And they're all connected through gravity in ways that scientists are still working to fully understand. Let's start with Saturn, because Saturn's response to Jupiter's explosion will be the most immediate and dramatic. Saturn is the second largest planet in our solar system, with 95 times Earth's mass. That sounds impressive until you remember Jupiter is 318 Earth masses. Saturn is roughly 1/3 Jupiter's mass. In the gravitational hierarchy of the solar system, Jupiter has always been the dominant force in the outer regions, and Saturn has been the second in command. The two planets orbit the Sun with a 2.51 ratio. Saturn takes about 29.5 Earth years to complete one orbit, while Jupiter takes 11.9 years. This means they align in roughly the same part of their orbits about once every 20 years. This configuration, called a Great Conjunction, has been observed and recorded by astronomers for thousands of years. In December 2020, we witnessed the closest Great Conjunction in nearly 400 years. Jupiter and Saturn appeared so close together in the night sky, they were almost touching. Astronomers around the world pointed their telescopes at the pair, marveling at seeing both planets and their moons in the same field of view. These conjunctions aren't just pretty to look at. They represent moments when the two planets' gravitational influences align, creating subtle perturbations in each other's orbits. Over billions of years, these perturbations have helped stabilize both planets' orbits. They pull on each other, nudge each other, keep each other in check. This gravitational relationship extends beyond just Jupiter and Saturn. There's something called the Nice Model, named after the French city, where it was developed in 2005. This model suggests that in the early solar system, about 500 to 600 million years after formation, the outer planets weren't where they are now. They were closer together, and their orbits were more circular. Then something happened. Gravitational resonances between Jupiter and Saturn caused their orbits to shift. Jupiter moved slightly inward, Saturn moved significantly outward, and as Saturn moved, it disturbed Uranus and Neptune, sending them careening outward as well. This migration triggered what we call the Late Heavy Bombardment, a period when the inner solar system was pummeled by comets and asteroids, explaining the crater-covered surfaces of the Moon, Mercury, and Mars. The Nice model is still debated, but most planetary scientists agree that Jupiter and Saturn's gravitational dance shaped the outer solar system. They're not just neighbors, they're partners in a billion-year gravitational choreography that determines where every outer planet orbits. When Jupiter explodes 1 month into our catastrophe timeline, Saturn begins to feel the effects. The first change is subtle. Saturn is currently about 655 million miles from where Jupiter was, depending on where both planets are in their orbits. The gravitational information about Jupiter's disappearance takes about 58 minutes to reach Saturn at light speed. But here's the thing about orbital mechanics: changes don't happen instantly. Saturn is moving at about 21,000 miles per hour in its orbit. That sounds fast, but at Saturn's distance from the Sun, orbital adjustments take time. When Jupiter's gravity suddenly vanishes, Saturn doesn't immediately fly off in a new direction. Instead, its orbit begins to slowly evolve in a new trajectory. Think of Saturn as a ball on the end of a string being swung around. The string is the Sun's gravity keeping Saturn in orbit. Jupiter's gravity is like someone occasionally tugging on the ball, adjusting its path slightly. When those tugs stop, the ball doesn't fly away. It continues circling, but its path slowly changes. The specific changes to Saturn's orbit would depend on where Saturn and Jupiter were positioned at the moment of explosion. In the worst-case scenario, if they were at conjunction close together, Saturn would experience a more dramatic change. If they were at opposition on opposite sides of the Sun, the change would be more gradual. But regardless of positioning, the end result is the same: Saturn's orbit becomes less stable. Here's where it gets mathematically interesting. Saturn's current orbit has an eccentricity of 0.06. Eccentricity is a measure of how elliptical an orbit is. 0 is a perfect circle, and 1 is a parabola that escapes the system entirely. Saturn's orbit is very close to circular, which is part of what makes our solar system stable. Without Jupiter's gravitational influence to maintain this near-circular orbit, Saturn's eccentricity would begin to increase. Not quickly. We're talking about changes that would unfold over decades and centuries. But the trend would be clear. Saturn's orbit would become more elliptical, bringing it slightly closer to the Sun at perihelion and slightly farther at aphelion. This has consequences. Saturn has 146 known moons, more than any other planet in our solar system. The 7 largest, Mimas, Enceladus, Tethys, Dione, Rhea, Titan, and Iapetus, are substantial worlds in their own right. Titan is larger than Mercury and has a thick atmosphere. Enceladus shoots geysers of water into space from a subsurface ocean. These moons exist in a delicate gravitational balance with Saturn. When Saturn's orbit begins to change, the moon's orbits are affected as well. Not catastrophically, at least not immediately. But over centuries, the accumulated changes would alter the moon's system. Some moons might drift slightly inward, others might migrate outward. In extreme cases, small moons might be lost entirely, either falling into Saturn or being ejected into independent solar orbits. Titan, the jewel of Saturn's moon system, would be particularly interesting to watch. Titan is the only moon in the solar system with a substantial atmosphere, thicker than Earth's in fact. Its atmosphere is mostly nitrogen with some methane, and the surface features lakes and rivers of liquid methane and ethane. It's one of the most Earth-like worlds we've discovered, despite being unimaginably cold at -290 degrees Fahrenheit. The Cassini mission, which orbited Saturn from 2004 to 2017, revealed Titan to be a world of incredible complexity. It has weather seasons, erosion, and a hydrological cycle, just with methane instead of water. It might even have prebiotic chemistry happening in those hydrocarbon lakes. If Saturn's orbit becomes more eccentric, Titan's distance from the Sun would vary more over the course of Saturn's year. This would affect Titan's climate. More elliptical orbit means more extreme seasons. Titan's methane lakes might freeze more deeply during colder periods, or evaporate more extensively during warmer periods. Over millennia, this could fundamentally alter Titan's environment. And Titan isn't the only moon at risk. Enceladus, that small moon with the geysers, is kept warm by tidal heating from Saturn. The same process that makes Io volcanic and keeps Europa's ocean liquid. If Saturn's orbit changes, the tidal heating patterns could change too. Enceladus might become more geologically active or less. Either way, the moon system we've studied for decades would begin to transform into something different. But Saturn's problems extend beyond its own moons. Remember that debris cloud expanding from Jupiter's explosion? By 1 month after the event, that cloud has grown enormous. It's spread across hundreds of millions of miles, and some of the fastest moving debris is approaching Saturn's orbit. Now, space is vast, and the debris is spreading in all directions. Most of it will miss Saturn entirely, but most isn't all. Saturn, with its enormous gravitational field, will act as a collector for debris passing anywhere near it. Chunks of what used to be Jupiter, ranging from dust particles to moon-sized fragments, will be captured or deflected by Saturn's gravity. Some debris will crash into Saturn's atmosphere, creating impact flashes visible from Earth. These impacts wouldn't significantly harm Saturn. It's too large, and the debris fragments are too small by comparison. But they would be spectacular to observe. Imagine dozens or hundreds of Shoemaker-Levy 9-style impacts, but spread over months and years as different debris trajectories intersect Saturn's orbit. Saturn's rings would be particularly vulnerable. Those magnificent rings made of countless particles of ice, ranging from grain-sized to house-sized, are already dynamic and evolving. Debris impacts would disrupt the rings, potentially creating new gaps, new features, new structures that astronomers would rush to study. The Cassini division, that prominent gap in Saturn's rings caused by gravitational resonances with Saturn's moons, might change. New material from Jupiter could be captured into the ring system, altering its composition and appearance. The rings we've admired for 400 years since Galileo first glimpsed them through his primitive telescope would begin to look different. Let's talk about the ice giants for a moment, Uranus and Neptune. These worlds are farther out, more distant, more mysterious. Uranus orbits at 1.8 billion miles from the Sun. Neptune is at 2.8 billion miles. They're so far away that Voyager 2, launched in 1977, didn't reach Uranus until 1986, and Neptune until 1989. And those brief flybys remain our only close-up looks at these worlds. Uranus is strange. It's tilted on its side, rotating with its axis nearly in the plane of its orbit. This means Uranus essentially rolls around the Sun like a ball, with each pole experiencing 42 years of continuous sunlight, followed by 42 years of darkness. No one is quite sure why Uranus is tilted this way. The leading theory is a massive collision early in the solar system's history, but it remains one of planetary science's great mysteries. Neptune is the windiest planet in the solar system, with storms reaching 1 in 200 miles per hour. It's also noticeably bluer than Uranus due to an unknown component in its atmosphere that absorbs red light. And Neptune has Triton, a large moon that orbits backward, retrograde, suggesting it was captured from the Kuiper belt rather than forming with Neptune. Both ice giants have mass about 15 to 17 times Earth's mass. They're much smaller than Jupiter and Saturn, but still significant. And both are far enough from Jupiter that the explosion's immediate effects would be minimal. But minimal doesn't mean none. Uranus is currently about 1.6 billion miles from Jupiter's position. Neptune is about 2.7 billion miles away. The gravitational changes would take hours to propagate to these distances. The debris cloud would take months or years to reach them, if it reaches them at all. Yet, over decades and centuries, both planets would feel the loss of Jupiter. The orbital resonances that stabilize the entire outer solar system would be broken. Uranus's orbit, Neptune's orbit, even their interactions with each other, all of it would begin to slowly drift into new configurations. Computer simulations of solar system dynamics have shown that removing Jupiter would make the outer planets' orbits chaotic over time scales of millions to hundreds of millions of years. Chaotic in mathematical terms doesn't necessarily mean catastrophic. It means unpredictable, sensitive to initial conditions. Small changes early on could lead to vastly different outcomes later. In some simulations, Uranus might migrate inward, possibly encountering Saturn. In others, Neptune might drift outward, its orbit becoming more eccentric. The specific outcomes would depend on the exact positions and velocities of all the planets at the moment Jupiter exploded. Tiny differences in initial conditions leading to dramatically different futures. This is called deterministic chaos, and it's a fundamental property of systems with three or more bodies orbiting each other. Isaac Newton discovered the two-body problem, one object orbiting another, could be solved perfectly. But add a third body, and the mathematics becomes unsolvable. We can only approximate simulate estimate. Jupiter's presence has kept that chaos in check for 4.5 billion years. Its massive gravity acted as an anchor, a stabilizing force that kept the other planets in predictable orbits. Without it, the outer solar system would enter a new phase, one where predictions become increasingly uncertain the farther into the future we look. By 1 month after Jupiter's explosion, none of this would be immediately obvious to observers on Earth. The outer planets would still be where we expect them. Their moons would still orbit normally. The rings of Saturn would look the same to the casual observer. But astronomers running orbital simulations would be seeing troubling results. Their predictions for where Saturn would be in 100 years would show increasing error bars. Predictions for 1,000 years would show Saturn could be in any of several different positions. Predictions for 10,000 years would be barely better than guesses. The outer solar system, that realm of cold and darkness that has remained stable for billions of years, would have entered an era of uncertainty. And while that uncertainty would unfold over timescales far longer than human lifetimes, the trajectory would be clear. The age of stability was over. A new, more chaotic era had begun. Yet, even as we contemplate these long-term changes in the outer solar system, there's a more immediate question that would be consuming everyone on Earth. What happens here? What would we see in our skies? How would our world change in the first year after Jupiter's explosion? Picture yourself standing outside on a clear night 1 year after Jupiter exploded. You look up at the sky, and for a moment, everything seems normal. The moon hangs bright and familiar. The constellations are where they've always been. But then you notice something different. Where Jupiter used to shine as a steady, brilliant point of light, there's nothing, just darkness. And scattered across the ecliptic, the path planets follow across our sky, there are new lights, faint, moving, multiplying. Those are asteroids, and they're getting closer. If you're finding this journey through cosmic catastrophe both fascinating and unsettling, you're not alone. Understanding these scenarios helps us appreciate the delicate balance that makes our existence possible. And if you'd like to continue exploring these cosmic mysteries with me, a like and subscribe means we can keep diving deep into the wonders and terrors of our universe together. Now, let's talk about what life on Earth would actually be like in that first year, because the changes wouldn't be abstract or distant. They would be visceral, visible, and increasingly frightening. Let's start with the most immediate visible change: the night sky. For thousands of years, humans have looked up at Jupiter. Ancient Babylonians tracked it meticulously, creating the first known astronomical records around 1800 BCE. The Romans named it after their king of the gods, recognizing its brightness and importance. Chinese astronomers called it the year star because its 12-year orbital period roughly matched their calendar cycle. In modern times, Jupiter is usually the fourth brightest object in our night sky after the Sun, Moon, and Venus. On particularly favorable oppositions, when Jupiter is closest to Earth, it can outshine even Sirius, the brightest star. It's bright enough to cast faint shadows on moonless nights in locations far from light pollution. When Jupiter explodes, that light doesn't simply vanish. For the first few weeks, the expanding debris cloud would actually make Jupiter appear brighter. The explosion would create a glowing nebula visible to the naked eye, expanding and dimming over months. By 3 months after the explosion, Jupiter would have faded to something resembling a diffuse nebula, similar to the Orion Nebula, but larger and closer. Amateur astronomers with backyard telescopes would be able to see structure within the cloud. Wisps eddies brighter regions where debris was more concentrated. By 6 months, Jupiter would have faded further, requiring binoculars or small telescopes to see clearly. The debris cloud would span several degrees of sky, about the width of your fist held at arm's length. It would continue expanding, dimming, dispersing. By 1 year, Jupiter would be barely visible even with professional telescopes. The debris would be so spread out, so diffuse that it would blend into the background of space. 4 billion years of existence erased from the night sky. For stargazers and amateur astronomers, this would be profoundly disorienting. Jupiter has been a constant companion in the night sky for all of human history. Ancient navigators used it. Medieval astronomers studied it. Modern backyard astronomers share views of it through their telescopes at star parties. Its absence would feel like losing an old friend, but the emotional impact would be the least of our concerns. Remember those asteroid orbital changes we discussed? By 1 year after Jupiter's explosion, the first consequences would be reaching Earth's vicinity. NASA's Center for Near-Earth Object Studies, based at the Jet Propulsion Laboratory in California, constantly tracks asteroids that might pose a threat to Earth. As of 2024, they've cataloged over 32,000 near-Earth asteroids. Of these, about 2,300 are classified as potentially hazardous asteroids, objects larger than 460 feet that come within 4.6 million miles of Earth's orbit. The system works well for a stable solar system. Astronomers discover an asteroid track it over multiple observations, calculate its orbit with high precision, and determine whether it poses any risk over the next 100 years. If it does, we have decades to prepare a deflection mission, like NASA's successful DART mission in 2022, that deliberately crashed into the asteroid Dimorphos and altered its orbit. But in a post-Jupiter world, this system breaks down. Within months of Jupiter's explosion, the number of near-Earth asteroids would begin to increase. Not dramatically at first, maybe a few dozen new discoveries per month, rather than the usual few dozen per year. But the trend would be clear and accelerating. By 6 months, astronomers would be detecting hundreds of new near-Earth asteroids. Objects that had been safely in the main belt for billions of years would now be crossing Earth's orbit. The catalog of potentially hazardous asteroids would double, then triple, then quadruple. By 1 year, the situation would be approaching crisis levels. Thousands of new near-Earth asteroids would be discovered, and more would be arriving constantly. The orbital tracking systems designed to handle dozens of objects would be overwhelmed by thousands. Worse, many of these asteroids would be on chaotic orbits, making long-term predictions difficult or impossible. Let me give you a specific scenario to illustrate the danger. Imagine an asteroid we'll call 2025 JX43. Before Jupiter's explosion, this asteroid orbited safely in the main belt, about 250 million miles from Earth. Its orbit was stable, predictable, no threat to anyone. When Jupiter exploded, the debris field expanded outward and a fast-moving chunk of what used to be Jupiter, let's say a fragment the size of a house, passed near 2025 JX43. The gravitational interaction was brief, lasting only hours, but it was enough to alter JX43's velocity by just 50 miles per hour. That's nothing in cosmic terms, about the speed of a car on a highway. But that 50 mph change applied at a distance of 250 million miles from Earth compounds over time. After 6 months, JX43 has drifted thousands of miles from where it would have been. After a year, it's millions of miles off its predicted course. And instead of remaining safely in the belt, it's now on an orbit that crosses Earth's path. JX43 is a kilometer wide, about 2/3 of a mile. If it hit Earth, it would release energy equivalent to 100,000 megatons of TNT. That's about 6,000 times more powerful than the largest nuclear weapon ever tested. The impact would excavate a crater 12 miles wide. If it hit an ocean, it would create tsunamis hundreds of feet high that would devastate coastlines thousands of miles away. If it hit land, it would throw enough dust into the atmosphere to cause regional climate disruptions lasting years. And JX-43 would be just one of thousands of asteroids on new unpredictable orbits. NASA and other space agencies would face an impossible task: track. Thousands of new threats calculate their orbits with limited observation, time to determine which ones pose the greatest risks, and somehow develop deflection missions for multiple asteroids simultaneously. We currently have the technology to deflect one asteroid if we have years of warning. We don't have the infrastructure to deflect dozens or hundreds, especially with only months of warning. The political and social implications would be profound. Where do you evacuate people to if an impact is predicted? How do you choose which asteroids to try to deflect and which to simply track and hope for the best? What happens to global cooperation if different nations perceive different levels of threat? In 2013, an asteroid only 66 feet across exploded over Chelyabinsk, Russia, with the force of 500 kilotons of TNT. The shockwave damaged thousands of buildings and injured about 1,500 people, mostly from broken glass. That asteroid was so small and so faint that no one detected it before it hit. Now imagine that instead of one Chelyabinsk event per decade, we're facing the possibility of one per year, or per month, or per week. But asteroids aren't the only concern. Let's talk about what would happen to Mars. Mars orbits between Earth and the asteroid belt at an average distance of about 140 million miles from the Sun. It's closer to the belt than Earth is, which means it's first in line for the new bombardment. Mars has already had a rough existence. Its small size, only about half Earth's diameter and a tenth of Earth's mass, meant it couldn't hold on to a thick atmosphere. Its lack of a global magnetic field, which Earth has due to our active molten core, meant solar winds stripped away much of the atmosphere Mars once had. Billions of years ago, Mars had liquid water on its surface. Rivers carved valleys, lakes filled impact craters. There might have been an ocean in the northern lowlands, but that water is gone now, frozen in the polar ice caps or locked underground as permafrost. The atmosphere is only about 1% the pressure of Earth's. So thin you'd need a spacesuit to survive, even if it were the right temperature. We've been exploring Mars with rovers and orbiters for decades. Spirit and opportunity, curiosity, perseverance. These robotic explorers have been slowly piecing together Mars's history, searching for evidence that life might have once existed there. We've also been planning to send humans to Mars. NASA's Artemis program aims to establish a sustainable presence on the Moon as a stepping stone to Mars. Private companies like SpaceX have ambitious plans for Mars colonization. The dream of becoming a multiplanetary species, of having a backup for humanity off Earth, has been centered on Mars. In a post-Jupiter world, all of that ends. Mars, being closer to the disrupted asteroid belt, would face an impact rate perhaps 10 times higher than Earth's. The planet's thin atmosphere provides almost no protection. Asteroids that would burn up in Earth's thick atmosphere would slam into Mars at full velocity. Any missions currently on Mars would face immediate danger. The Perseverance rover, exploring Jezero crater and collecting samples for future return to Earth. The Ingenuity helicopter, the first aircraft to fly on another planet. The InSight lander, measuring Mars quakes. All of them would be at risk from increased meteor activity. Within 1 year, it's likely at least one of our Mars assets would be damaged or destroyed by an impact. These aren't small losses. Each mission costs billions of dollars and represents years of work by thousands of scientists and engineers. More importantly, they represent humanity's presence on another world. Losing them would mean losing our eyes and ears on Mars at the precise moment we need them most. Human missions to Mars would be canceled indefinitely. The risk would be simply too high. Even getting to Mars would be dangerous, as spacecraft would need to traverse an increasingly crowded region of space filled with debris and displaced asteroids. The dream of Mars colonization would die before it began. Think about what this means for humanity's future. Right now, we're a single-planet species. Every human who has ever lived, except for brief visits to near-Earth orbit and the Moon, has lived on Earth. If a truly catastrophic event happened here, a massive asteroid impact, a supervolcano eruption, a nuclear war, a pandemic more severe than anything we've experienced, human civilization and possibly humanity itself could end. Mars represented hope, not just the scientific hope of discovering past life, but the existential hope of becoming a multi-planetary species. If Earth became uninhabitable, humans on Mars could survive. The species would continue. In a post-Jupiter world, that hope evaporates. We would be trapped on Earth, facing an increasing bombardment from space, with no escape route available. But even here on Earth, the effects would extend beyond asteroid threats. Let's talk about something most people haven't considered: tides and orbital stability. Jupiter's gravity, even from 500 million miles away, does affect Earth. The effect is tiny, far smaller than the Moon's tidal influence, but it's measurable. Jupiter's gravity creates tidal forces on Earth of about 1/10,000,000th the strength of the Moon's tidal force. That's small enough that you'd never notice it directly. But over millions of orbits, these tiny nudges add up. More significantly, Jupiter's gravity helps stabilize Earth's axial tilt. Earth is currently tilted at 23.5 degrees relative to its orbital plane around the Sun. This tilt gives us our seasons. Summer in the northern hemisphere when the North Pole tilts toward the Sun, winter when it tilts away. But that tilt isn't fixed. It oscillates slightly, varying between 22.1 and 24.5 degrees over a cycle of about 41,000 years. This is one of the Milankovitch cycles, named after Serbian scientist Milutin Milankovic, who discovered them in the 1920s. These cycles affect Earth's climate, contributing to Ice Age timing. Computer simulations have shown that without Jupiter, Earth's axial tilt would be far less stable. Mars provides a cautionary tale. Without a large moon and without Jupiter's stabilizing influence, Mars's axial tilt varies wildly over millions of years, swinging from 15 degrees to 35 degrees. These wild swings cause dramatic climate shifts. Earth, protected by both our large moon and Jupiter's distant gravity, has remained stable. Our tilt varies by only 2.4 degrees over 41,000 years. This stability has been crucial for the development of complex life. Stable climates allow evolution to proceed without constant catastrophic resets. In a post-Jupiter world, Earth's axial tilt would begin to vary more over millions of years. Not immediately, the changes would be gradual, but the trend toward instability would be clear. Future ice ages might be more severe. Future warm periods might be more extreme. The stable climate that allowed human civilization to flourish over the last 10,000 years would become less reliable over deep time. By the end of the first year after Jupiter's explosion, humanity would be facing a grim new reality. The night sky would be forever changed. The asteroid threat would be escalating. Mars exploration would be suspended indefinitely. And scientists would be warning about long-term climate instability due to axial tilt variations. News headlines would dominate global consciousness. Emergency meetings at the United Nations, space agencies pooling resources, observatories working around the clock to track new threats. The public would be caught between denial and panic, with some people insisting it couldn't be that bad, while others prepared for the worst. But as terrible as the first year would be, it would only be the beginning, because over the next century, as more and more asteroids found their way into Earth-crossing orbits, the true scale of the catastrophe would become apparent. Imagine living your entire life knowing that any day without warning, the sky could light up with a fireball announcing the end of your city, your nation, perhaps your species. This isn't science fiction. This is the reality Earth would face 1 century after Jupiter's explosion. A world where the asteroid that killed the dinosaurs isn't a once in 100 million years event, but a once in 100,000 years event. And where smaller city-destroying impacts could happen within any given lifetime. We're now deep into the long-term consequences of losing our guardian planet, and the picture is becoming clearer and more frightening. If these thought experiments help you appreciate the cosmic balance that protects us, I'd be grateful if you'd share this journey with others who might find it as fascinating as you do. Let's talk about what happens over the century following Jupiter's explosion, because this is where statistical probabilities become lived experiences. Scientists estimate impacts based on probability curves. For example, the Torino scale developed in 1999 by MIT professor Richard Binzel rates asteroid threats from to 10. 0 means no hazard. 10 means certain collision with global catastrophe. The scale helps communicate risk to the public without causing panic. In our current solar system, most known asteroids rate 0 on the Torino scale. A few rate 1 or 2, meaning close passes but no real danger. We've never had an asteroid rate above 4 while being tracked. And even that would only represent a close encounter worth attention from astronomers. In a post-Jupiter world, the Torino scale would need to be recalibrated. Within a century of Jupiter's explosion, we would likely have dozens of asteroids simultaneously rated at 3 or higher. Multiple objects would pose real quantifiable threats at any given time, and the number would keep growing. Let's ground this in specific historical examples so you can understand the scale we're talking about. On June 30th, 1908, something exploded over the Tunguska region of Siberia with the force of 10 to 15 megatons of TNT. The blast flattened 80 million trees over 830 square miles. If you've ever seen photos of the aftermath, it's haunting. Trees knocked down in a radial pattern, all pointing away from the explosion's center like a colossal stamp pressed into the forest. The Tunguska event was caused by an asteroid or comet fragment estimated to be only 120 to 200 feet across. It exploded in the atmosphere before hitting the ground, which is why there's no impact crater. The air burst was devastating enough. If Tunguska had happened over London, Paris, New York, or Tokyo instead of remote Siberia, millions of people would have died. The entire city would have been obliterated. Buildings would have been vaporized at the center, flattened for miles around. The death toll would have exceeded any natural disaster in human history. Events like Tunguska are estimated to occur about once every 300 to 1,000 years. We got lucky in 1908 that it hit an unpopulated area. We got lucky that no Tunguska-scale event has happened over a city in recorded history. In a post-Jupiter world, Tunguska-scale events would happen every 3 to 10 years. Think about that. Every decade somewhere on Earth, an explosion equivalent to 10 megatons would occur. Most would hit oceans. Earth is 71% water after all. But even ocean impacts create problems. A Tunguska-scale airburst over an ocean would generate tsunamis, disrupt shipping lanes, and potentially damage coastal cities. And statistically, within a century, several impacts would hit land. Some would hit populated areas. Now, let's scale up. The Chicxulub impact that killed the dinosaurs was caused by an asteroid about 6 miles wide. It released energy equivalent to 100 million megatons. The impact created a crater 93 miles wide and triggered global devastation. Dust and debris blocked out the sun for years. Temperatures plummeted. Photosynthesis stopped. The food chain collapsed from the bottom up. About 75% of all species on Earth went extinct. Chicxulub-scale impacts are estimated to occur roughly once every 100 million years. Humans have never witnessed one. Civilization has existed for only about 10,000 years. We've built our entire world during a period of unusual geological quiet. In a post-Jupiter world, Chicxulub-scale impacts would occur about once every 100,000 years. Now, 100,000 years still sounds like a long time. Modern humans Homo sapiens have existed for about 300,000 years. So even in a post-Jupiter world, we might get lucky. We might avoid the big one for many generations. But here's the thing about statistical probability. It's random. The impact could happen in year 1 or year 100, 1,000, or anywhere in between. The average is 100,000 years, but that doesn't mean impacts are evenly spaced. They're governed by chaos and chance. And more importantly, there's a whole spectrum of impacts between Tunguska and Chicxulub. Let's explore that spectrum. A half-mile-wide asteroid much smaller than Chicxulub, but much larger than Tunguska, would release energy equivalent to 10,000 megatons. That's about 600 times more powerful than the largest nuclear weapon ever tested. An impact would excavate a crater 6 miles wide. If it hit an ocean, the resulting tsunamis would devastate coastlines for thousands of miles. If it hit land, the regional destruction would be total, and the global effects would cause a temporary cooling of Earth's climate, failed harvests, and famines, affecting billions of people. Events of this scale currently occur about once every 100,000 years. In a post-Jupiter world, they'd happen every 100 to 1,000 years. The historical parallel is sobering. In 1815, Mount Tambora in Indonesia erupted, throwing massive amounts of ash into the atmosphere. The following year, 1816, became known as the Year Without a Summer. Crops failed across Europe and North America. Snow fell in June in New England. Tens of thousands of people died from starvation and disease. Global temperatures dropped by about 1 degree Fahrenheit. Just 1 degree was enough to cause worldwide catastrophe. A half-mile asteroid impact would have effects similar to Tambora, but more severe and affecting a larger area. And instead of being a once-in-several-centuries volcanic event, it would be a recurring threat every few centuries. Now, imagine you're a human living 100 years after Jupiter's explosion. You're born into a world that has already experienced several Tunguska-scale events in living memory. Your grandparents remember when an airburst destroyed a city in South America. Your parents were teenagers when another impact created a new lake in Central Asia, displacing millions of people. Asteroid detection and tracking systems run 24/7. Every government maintains emergency response plans for impacts. Coastal evacuation procedures are practiced regularly like fire drills. Insurance companies have entire divisions calculating asteroid impact probabilities for different regions. Real estate values reflect impact risk. Areas perceived as safer command premium prices. Space agencies maintain a fleet of deflection spacecraft ready to launch at short notice. The technology works usually. NASA's DART mission proved we can alter an asteroid's orbit, but it requires years of warning, precise calculations, and significant resources. And we can't deflect everything at once. Which brings us to a terrible calculation triage. When multiple asteroids threaten Earth simultaneously, authorities have to decide which ones to deflect, and which ones to simply track and evacuate areas beneath their predicted impact zones. The decision matrix is brutal. How many people are in the impact zone? How large is the asteroid? How certain are we of the trajectory? How much would deflection cost? Can we afford to deflect this one and still have resources for the next threat? These decisions would be made in government offices and international committees. The public wouldn't always know the full extent of the threats being managed. Information would be carefully controlled to prevent panic, but rumors would spread. Trust in authorities would erode. Social cohesion would fray. Some nations would fare better than others. Countries with advanced space programs, robust early warning systems, and effective evacuation infrastructure would have advantages. But no nation would be immune. The asteroid threat doesn't respect borders. International cooperation would become both more necessary and more difficult. Space agencies would need to share data pool resources, coordinate deflection missions. But national interests would still conflict. Which country's asteroid gets deflected first? Who pays for international missions? What happens when a deflection mission saves one nation but increases risk for another by altering the asteroid's trajectory? We saw hints of these challenges during the COVID-19 pandemic, a global threat requiring international cooperation, but hampered by national politics, unequal resources, and competing interests. Now, imagine that scenario playing out repeatedly with existential stakes over decades. Let's talk about the psychological impact, because I think this is something we often overlook in disaster scenarios. Human psychology evolved in a world where most threats were immediate and visible. A predator in the bushes, a rival tribe, a storm approaching. We're good at responding to threats we can see, hear, and touch. We're not good at responding to statistical abstract threats. Climate change provides a modern example. The threat is real, supported by overwhelming scientific evidence, but it's gradual and abstract. Many people struggle to treat it as urgent because they can't see or feel the danger in their daily lives. Asteroid threats in a post-Jupiter world would be different. They'd be concrete and recurring. After the first few major impacts, the threat would be visceral and undeniable, but the randomness would be psychologically devastating. Psychologists have studied the effects of living under constant threat. Studies of populations in war zones, earthquake-prone regions, and areas with frequent natural disasters show consistent patterns: chronic stress, anxiety disorders, PTSD, decreased life satisfaction, difficulty planning for the future. Now, extend that to the entire global population. Everyone on Earth living with the knowledge that any day could bring an impact announcement. Children growing up in a world where asteroid drills are as common as fire drills. Couples debating whether it's ethical to have children in such a dangerous world. The birth rate would likely decline. Why bring children into a world with such uncertainty? Economic growth would stagnate as long-term investments become riskier. Cultural production might flourish. Humans often create intensely during dangerous times. Or it might decline as people focus on immediate survival rather than art and philosophy. Some people would become fatalistic. If death could come from the sky at any moment, why plan? Why save? Why build? Just live for today. Others would become obsessive about safety, constantly checking asteroid tracking websites, building bunkers, preparing for the worst. Religious interpretations would vary. Some would see the asteroid threat as divine punishment or a test of faith. Others would lose faith entirely. How do you reconcile a benevolent deity with random death raining from space? These are ancient theological questions, but they'd take on new urgency. Science fiction has imagined post-apocalyptic worlds, but usually after a single catastrophic event. What we're describing is different a world in permanent crisis, where the apocalypse hasn't happened yet, but could happen at any time. It's not the aftermath of disaster. It's the endless anticipation of disaster. Would human civilization survive this? Probably. We're remarkably adaptable. We survived ice ages, plagues, wars, famines. We'd develop new technologies, new social structures, new ways of coping. Life would go on, but it would be diminished. Resources that could go toward curing diseases, eliminating poverty, exploring the cosmos, creating art. All of that would be diverted to asteroid detection and deflection. Humanity's potential would be consumed by the need to simply survive. And here's what makes it truly tragic. It would all be because we lost Jupiter, our guardian, our protector, the planet. Most people never think about that has been quietly shielding us for billions of years. 1 century after Jupiter's explosion, humanity would be surviving, but barely thriving. We'd be locked in an endless struggle against a threat we didn't create and can't eliminate. We'd be using all our ingenuity and resources just to maintain the status quo rather than reaching for the stars. But even that comparison to our current civilization understates the full scope of what would be lost. Because the impact of Jupiter's absence extends beyond asteroids, beyond human concerns, beyond even this century. The effects ripple forward through deep time, affecting Earth's geology, climate, and the very conditions that make complex life possible. Let's step back from human time scales and look at something almost incomprehensible: deep time. 1,000 years from now, 10,000 years, 100,000, a million. Time periods so vast that entire civilizations rise and fall, continents drift, ice ages come and go. And through all of that deep time, one constant remains in a post-Jupiter world. Earth is fundamentally changed, not destroyed, but diminished. A planet that could have been so much more trapped in a new reality by the absence of its guardian. The story of Earth's transformation over millennia is ultimately the story of what makes a planet habitable, and I think understanding that helps us see our own world with fresh eyes. These long-view perspectives are what this channel is all about, so if you're finding value in this cosmic journey, your support means we can keep exploring together. To understand what Earth loses over deep time without Jupiter, we need to talk about something called the habitable zone. But not the way you might expect. Most people have heard of the habitable zone, sometimes called the Goldilocks zone. It's the region around a star where a planet can maintain liquid water on its surface. Too close to the star, and water boils away. Too far, and it freezes. Earth sits comfortably in the Sun's habitable zone, which extends from roughly 0.95 AU to 1.37 AU. 1 AU, or astronomical unit, is the distance from Earth to the Sun, about 93 million miles. But there's another kind of habitable zone that scientists have been discussing since the 1990s, and it's far more nuanced. It's called the circumstellar habitable zone, with planetary system architecture constraints. That's a mouthful, so let's break it down. The idea is, this being at the right distance from your star is necessary, but not sufficient for complex life. You also need the right planetary system architecture. You need giant planets in the right places doing the right jobs. In 2000, paleontologist Peter Ward and astronomer Donald Brownlee published a book called Rare Earth: Why Complex Life is Uncommon in the Universe. It was controversial, and many scientists disagreed with their conclusions, but it raised crucial questions that have shaped astrobiology ever since. Ward and Brownlee argued that while simple microbial life might be common in the universe, complex life, anything beyond bacteria, requires an extraordinary combination of circumstances. One of those circumstances is having a Jupiter-like planet in the right orbit. They called it the Jupiter as shield hypothesis. The idea is that without a giant planet to intercept or deflect asteroids and comets, a terrestrial planet would be bombarded so frequently that complex life could never gain a foothold. Every time life started to diversify to become more complex, an impact would reset the evolutionary clock. This hypothesis has been debated extensively. Some computer simulations suggest Jupiter actually increases Earth's impact rate by disturbing comets in the Oort cloud. Other simulations show Jupiter dramatically decreases impacts. The truth probably lies somewhere in between and depends heavily on the specific orbital configuration. But here's what we know for certain from Earth's geological record: the frequency of large impacts has decreased over time. Early Earth during the late heavy bombardment about 4 billion years ago was hit constantly. Gradually, the bombardment decreased as the solar system cleaned itself up. By about 3.8 billion years ago, conditions had stabilized enough for life to begin. And once life began, it had time. Billions of years of relatively stable conditions, punctuated by occasional catastrophic impacts, but with long enough intervals between impacts for life to recover, diversify, and become more complex. The Cambrian explosion about 540 million years ago saw the sudden appearance of most major animal groups in the fossil record. This wasn't really an explosion in human terms. It took place over about 25 million years. But in geological time, it was remarkably rapid. Why did it happen then and not earlier? There are many theories, but one factor was certainly stability. By the Cambrian Earth had been relatively impact-free for hundreds of millions of years. Ecosystems could develop complexity. Evolution could explore new body plans without being constantly reset by global catastrophes. Now imagine Earth in a post-Jupiter solar system. The impact frequency doesn't just stay at late heavy bombardment levels. It's actually worse because the asteroid belt is now actively destabilized, rather than just containing leftover primordial debris. Over 1 million years, Earth would be hit by dozens of civilization-ending impacts. Over 10 million years, hundreds. Each impact would cause massive extinctions. Each extinction would reset ecological complexity. Let's look at what we know about extinction and recovery from Earth's history. The Permian-Triassic extinction about 252 million years ago was the worst mass extinction in Earth's history. Roughly 96% of marine species and 70% of terrestrial vertebrate species went extinct. The cause is still debated: massive volcanic eruptions in Siberia, ocean anoxia methane released from the seafloor. But the effects are clear from the fossil record. It took about 10 million years for biodiversity to recover to pre-extinction levels. 10 million years for ecosystems to rebuild their complexity. During that recovery period, the planet was dominated by simpler, more generalist species. Specialized species, complex food webs, intricate ecological relationships. All of that had to evolve again from scratch. Now, consider that in a post-Jupiter world, civilization-ending impacts would occur roughly every 100,000 years. That's 100 such impacts per 10 million years. Each one wouldn't be as severe as the Permian-Triassic extinction. Most would be more like the Chicxulub impact that killed the dinosaurs, causing perhaps 75% species extinction, rather than 96%. But they would happen far more frequently. The result would be what scientists call a diversity pump running in reverse. Instead of life gradually becoming more complex and diverse over time, complexity would be capped. Any time life approached the complexity level we see today, an impact would knock it back down. Complex life might never evolve past a certain point. Large animals would be particularly vulnerable. They have smaller populations, slower reproduction rates, and higher energy requirements. All of those factors make them more susceptible to extinction. In a high-impact environment, the largest animals might never exceed the size of a dog. The age of dinosaurs, the age of mammals. None of it would happen. And intelligence is expensive. Brains consume enormous amounts of energy. Humans use about 20% of our caloric intake just to power our brains. Large brains only evolve when there's enough stability and resources to support them. In a post-Jupiter world, the evolutionary pressure would favor rapid reproduction and adaptability, not intelligence. Think cockroaches, not humans. Species that can bounce back quickly from catastrophes, that can survive on minimal resources, that don't invest heavily in individual offspring. The path that led from early primates to humans took about 7 million years. It required relatively stable conditions, abundant resources, and freedom from global catastrophes. In a post-Jupiter world, that 7 million year window would almost certainly be interrupted by multiple extinction events. Humanity as we exist today would never evolve. Let's talk about Earth's climate over these long timescales because it's affected in ways most people don't consider. Earth's climate is influenced by many factors: solar output, atmospheric composition, ocean currents, volcanic activity, and, yes, orbital parameters. We mentioned earlier that Jupiter helps stabilize Earth's axial tilt. Without Jupiter, that tilt would vary more wildly over millions of years. But there's another effect: gravitational perturbations on Earth's orbit itself. Earth's orbit around the Sun isn't perfectly circular. It has an eccentricity of about 0.0167. very close to circular, but not quite. This eccentricity varies over time in a cycle of about 100,000 years, from nearly circular to slightly more elliptical and back. This is another Milankovitch cycle, and it affects how much solar radiation Earth receives. Currently, Earth is closest to the Sun in January and farthest in July. The difference is only about 3 million miles, but it affects seasonal intensity. Southern Hemisphere summers, when Earth is closest to the Sun, receive slightly more solar energy than Northern Hemisphere summers. These orbital variations are believed to be one of the pacing mechanisms for ice ages. When multiple Milankovitch cycles align in ways that reduce summer insolation at high northern latitudes, ice sheets begin to grow. When the cycles align to increase summer insolation, ice sheets melt. Jupiter's gravity helps regulate these cycles, keeping them within bounds that allow for ice ages but not snowball Earth events where the planet freezes completely. Without Jupiter, the cycles would become more chaotic. Computer simulations suggest that over tens of millions of years, Earth's orbital eccentricity could increase significantly. Instead of varying between 0.0055 and 0.2679 as it does now, it might vary between near 0 and 0.1, or even higher. An eccentricity of 0.1 means Earth's distance from the Sun would vary by about 20 million miles over the course of a year. That's a significant change in solar radiation. Seasons would become more extreme. Winters would be brutally cold. Summers would be scorching hot. Life would adapt, of course. Life is remarkably resilient. But the adaptation would favor extremophiles, organisms that can survive in harsh conditions, rather than the delicate specialized species that make up Earth's current biodiversity. Coral reefs, for example, are incredibly sensitive to temperature changes. A few degrees too warm, and corals bleach and die. In a world with more extreme seasonal variations, coral reefs might never evolve at all. Rainforests require stable, warm, wet conditions. With more extreme climate variations, rainforests might be replaced by more hardy, less diverse ecosystems. The ocean itself would be affected. Ocean currents are driven partly by temperature differences between the equator and poles. More extreme seasonal variations would create more variable currents affecting marine ecosystems globally. And all of this is happening while Earth is also being bombarded more frequently by asteroids. The combination is devastating. Climate stress plus impact stress equals a planet where complex life struggles to maintain a foothold. Here's a thought experiment that might help you grasp the scale of what we're discussing. Imagine you're a geologist a billion years from now in an alternate universe where Jupiter exploded in 2025. You're studying Earth's rock layers, trying to understand our planet's history. You would see something unprecedented in planetary science, a geological record showing repeated mass extinctions at intervals of only 100,000 to 1 million years. The normal pattern on Earth, long periods of stability punctuated by rare catastrophes, would be replaced by constant catastrophe. Each impact would leave a signature, an iridium layer like the one Luis and Walter Alvarez discovered in 1980 that proved an asteroid killed the dinosaurs, shocked quartz crystals, spherules of melted rock, signs of massive fires, then a period of recovery as life rebuilt. Then another impact layer, and another, and another. The rock record would tell the story of a planet under siege, and the biodiversity recorded in those rocks would be much lower than Earth's actual history. Fewer species, simpler ecosystems, a planet that never reached its full potential. This future geologist would probably hypothesize that something was wrong with this solar system's architecture. They might look at other planetary systems, compare them, and realize this system is missing its guardian giant. And without that guardian, this planet was doomed to mediocrity. Let me share something that puts all of this in perspective. The Drake equation. In 1961, astronomer Frank Drake developed an equation to estimate the number of active communicative extraterrestrial civilizations in the Milky Way galaxy. The equation multiplies together several factors: the rate of star formation, the fraction of stars, with planets, the number of habitable planets per star system, the fraction where life develops, the fraction where intelligent life evolves, the fraction that develops detectable technology, and the length of time such civilizations remain detectable. Scientists love to debate the Drake equation. Every factor is uncertain, and the final answer ranges from "we're alone" to "the galaxy is teeming with civilizations." But one factor is particularly relevant to our discussion: the fraction of life-bearing planets where intelligent life evolves. If Jupiter-like planets and Jupiter-like orbits are required for intelligence to evolve, that dramatically reduces this fraction. It means most life-bearing planets are stuck at bacterial or simple multicellular levels. Intelligence becomes not just rare, but extremely rare. This has profound implications for SETI, the search for extraterrestrial intelligence. Maybe the reason we haven't detected alien civilizations isn't because they're hiding or extinct or too far away. Maybe it's because planetary systems like ours, with the right architecture to allow intelligence to evolve, are incredibly uncommon. Earth in a post-Jupiter world would be an example of what most life-bearing planets look like: alive but simple, populated but not intelligent, full of bacteria and simple plants and small animals, but forever missing the spark of consciousness that asks, why? Over 1 million years, Earth would settle into its new normal. Life would adapt to the higher impact frequency. Ecosystems would evolve strategies for rapid recovery. The planet would be alive, dynamic, changing. But it would be a diminished Earth. A planet that could have harbored dinosaurs, redwood forests, coral reefs, wolves, whales, and humans. Instead, hosting a simpler menagerie of resilient but unremarkable species. The tragedy isn't that life would end. Life is tough. Life would continue. The tragedy is that life would never become all it could be. Like a child with enormous potential who never gets the stable environment needed to flourish, Earth would be locked into underachievement by circumstances beyond its control. And at the heart of those circumstances would be a simple truth: the guardian was gone. The protector that had watched over Earth for 4.5 billion years had vanished. And without it, everything changed. But here's what makes this thought experiment so powerful. It hasn't happened. Jupiter is still there, still protecting us, still invisible to most people's daily awareness. And understanding what we would lose helps us appreciate what we have. So, here we are at the end of our journey through catastrophe. We've watched Jupiter explode. We've seen moons destroyed and asteroid orbits shattered. We've followed the consequences through years, centuries, and millennia. We've imagined Earth transformed from a world of incredible biodiversity into something simpler, harsher, diminished. And now it's time to ask the most important question of all. What does this impossible scenario teach us about the real world we actually inhabit? Let me take you back to a moment in 1610. Galileo Galilei, looking through his crude telescope at Jupiter, discovering those 4 moons. He had no idea what he was really seeing. He didn't know those moons were worlds unto themselves. He didn't know Jupiter was a failed star, 318 times more massive than Earth. He certainly didn't know that Jupiter was protecting Earth from cosmic bombardment. He just saw 4 points of light moving around a bright planet, and he understood, we are not the center of everything. That moment of humility changed human history. It opened the door to modern science, to understanding our place in the cosmos, to seeing ourselves as part of something much larger. 400 years later, we've learned so much more. The Voyager missions in 1979 showed us Jupiter's complexity up close. The Galileo orbiter spent 8 years studying the Jovian system from 1995 to 2003. The Juno mission arriving in 2016 has been sending back data that continues to surprise us. discovering that Jupiter's atmosphere is far more chaotic than we imagined, that its magnetic field has multiple poles, that its interior is stranger and more complex than our models predicted. Every mission teaches us something new, and collectively, they've revealed a profound truth. Jupiter isn't just another planet, it's the reason we're here. Think about the chain of unlikely events that led to human existence. The sun had to form with the right mass, not too large, not too small. Earth had to form at the right distance, in the habitable zone where water can exist as a liquid. Earth needed to have the right composition, enough heavy elements to form a solid surface, enough volatiles to create an atmosphere and oceans. But all of those conditions, while necessary, weren't sufficient. Earth also needed time, billions of years of relative stability, time for chemistry to become biology, time for single cells to become complex organisms, time for fish to crawl onto land, for dinosaurs to rule and fall, for mammals to diversify, for primates to develop larger brains, for humans to emerge and build civilizations. And that time was a gift from Jupiter. Every impact Jupiter prevented was an extinction event that didn't happen. Every comet it deflected was a catastrophe averted. For 4.5 billion years, Jupiter has been out there in the darkness, doing its job, asking nothing in return. It's humbling, isn't it? To realize that our existence depends on a planet most people barely think about. When you look up at the night sky, you see the moon. Beautiful, close, obviously important. You might see Venus brilliant and bright. You probably notice Mars during good viewing periods, that distinctly red point of light. But Jupiter is just another dot. Bright, yes. Easy to find if you know where to look. But to most people, it's just another planet. Not special, not particularly interesting. Certainly not something that affects their daily lives. And yet, without it, none of us would be here. This is what I call the problem of invisible protection. We humans are very good at valuing things we can see and touch. We appreciate the atmosphere because we breathe it. We value the ocean because we see it, swim in it, eat from it. We protect forests because we can walk through them and witness their beauty. But how do you value something that protects you by preventing things that never happen? How do you appreciate asteroid impacts that never occurred, extinctions that never took place, disasters that were averted before you even knew they were possible? Jupiter is like the best kind of security system, so effective that you never notice it's there. And the danger of invisible protection is that we take it for granted. We assume it will always be there. We forget to be grateful. Let me tell you about something called the rare earth hypothesis in more detail, because I think it ties everything together beautifully. Peter Ward and Donald Brownlee's book examine not just whether life exists elsewhere in the universe, but whether complex life, animals, plants, fungi, anything multicellular, is common or rare. Their conclusion was controversial. They argued that while simple microbial life is probably common, complex life requires such an extraordinary combination of circumstances that it might be extremely rare. What are those circumstances? Let's count them. You need a star of the right type. Not too large, not too small, not too variable. You need a planet at the right distance. You need that planet to have the right mass. Too small, and it can't hold an atmosphere; too large, and it becomes a gas giant. You need plate tectonics to recycle nutrients and regulate climate. You need a large moon to stabilize axial tilt. You need the right atmospheric composition. You need liquid water, and you need a Jupiter. Critics of the rare Earth hypothesis point out that we have a sample size of 1. We only know one planet with complex life: Earth. We can't know how common or rare our configuration is until we study many other planetary systems in detail. That's fair. Science requires larger sample sizes. But here's what we've learned from exoplanet research over the past 3 decades since the first confirmed exoplanet discovery in 1992. We've now discovered over 5,000 exoplanets. That's an incredible data set. And what have we learned planetary systems are wildly diverse. Many have hot Jupiters, gas giants orbiting extremely close to their stars. Many have super-Earths, planets larger than Earth but smaller than Neptune in configurations we don't have in our solar system. Many have high eccentricity orbits planets on wildly elliptical paths. Our solar system, with its gas giants and distant circular orbits, its small rocky planets close to the star, its relative stability, appears to be uncommon. Not unique probably, but not typical either. This doesn't prove the rare Earth hypothesis, but it suggests that planetary systems like ours with Jupiter in the right place doing the right job might be less common than we once thought. And if complex life requires that specific architecture, then complex life might be rare indeed. Imagine the implications. The galaxy contains 100 to 400 billion stars. If even 1% of them have planets, and we now know most stars have planets, that's billions of planetary systems. But if only a tiny fraction of those systems have the right architecture for complex life, the galaxy might contain millions of worlds with bacteria, but only dozens or hundreds or thousands with animals. And if intelligence requires even more specific conditions, not just any complex life, but the right evolutionary pressures, the right environmental stability, the right sequence of events, then intelligent civilizations might be separated by thousands of light years. We might be one of a handful of technological civilizations in the entire galaxy. Not because life is rare, but because the path from microbes to intelligence requires winning the cosmic lottery multiple times in a row. And one of the lottery tickets Earth won was Jupiter. Now, I want to address something important. Some of you might be thinking, this is all very interesting, but it's hypothetical. Jupiter isn't going to explode. Why spend time imagining impossible scenarios? And you're right, Jupiter isn't going to explode. This entire thought experiment is physically impossible given what we know about planetary physics. But that's not really the point. The point is to understand what we have by imagining what we would lose. It's the same reason we study history, not to change the past, but to understand the present. It's why we run computer simulations of disasters. Not because we want them to happen, but so we can prepare and appreciate the times when they don't. By imagining a world without Jupiter, we come to appreciate the world with Jupiter. By understanding how fragile the conditions for complex life are, we come to value those conditions more deeply. And there's a practical application too. As we search for life on other worlds, in our solar system and beyond, understanding the role of planetary architecture helps us know where to look. Europa, one of Jupiter's moons that we watched get destroyed in our thought experiment, might harbor life in its subsurface ocean right now in the real world. Enceladus, a moon of Saturn, might as well. These are some of the most exciting targets in the search for extraterrestrial life precisely because they demonstrate that life might exist in unexpected places. But when we search for complex life, for intelligence, for civilizations that might communicate with us, the Jupiter factor matters. We should focus on planetary systems with architectures similar to ours. Systems with giant planets in the right orbits providing protection and stability to inner rocky worlds. The James Webb Space Telescope launched in 2021 is beginning to characterize exoplanet atmospheres. We're looking for biosignatures, chemical signs that life might exist on distant worlds. In the coming decades, we'll get better at not just finding exoplanets, but understanding them. And as we do, I suspect we'll find that Ward and Brownlee were at least partially right. Complex life, while perhaps not as rare as they suggested, is special. It requires getting many things right. And one of those things is having a guardian giant in the outer solar system. Let me leave you with a final thought because I think it's the most important one. Every time you look up at the night sky and see Jupiter, that bright, steady point of light, you're looking at the reason your ancestors survived long enough to give birth to you. You're looking at the reason dinosaurs had time to evolve and diversify before their eventual extinction. You're looking at the reason mammals could flourish in the aftermath. You're looking at the reason early humans could develop agriculture, build cities, invent, writing, create civilization. You're looking at the reason everything you've ever known exists. And Jupiter asks nothing in return. It doesn't demand gratitude or worship. It doesn't require payment or sacrifice. It just sits out there 500 million miles away, massive and majestic, doing what it has done for billions of years, protecting, guarding, allowing life on Earth to flourish. In a way, Jupiter is the ultimate symbol of invisible infrastructure, like the water treatment plants that keep your drinking water safe, like the electrical grid that powers your home, like the complex supply chains that deliver food to your grocery store. Jupiter is essential but unnoticed. It works perfectly, so we never think about it. But every now and then, it's worth stopping and thinking about it. It's worth looking up at that bright dot in the night sky and feeling genuine gratitude, not religious gratitude. Jupiter doesn't care about our feelings, but the kind of gratitude you feel when you truly understand how lucky you are, how improbable your existence is, how many things had to go exactly right for you to be here reading this, thinking these thoughts. The universe is vast and old. Stars have burned and died. Galaxies have collided. Black holes have consumed entire star systems. And through it all, in one quiet corner of an ordinary galaxy, a yellow star formed with just the right planetary arrangement. A failed star, not quite massive enough to ignite, settled into a distant orbit. And on a small rocky planet in the inner system, chemistry became biology, and biology became complexity, and complexity became consciousness. And that consciousness could look up at the sky, see that failed star still orbiting loyally after billions of years, and understand, I am here because you are there. That's the real lesson of our thought experiment. Not the destruction we imagine, but the protection we experience. Not the catastrophe that could have been, but the stability that is. Jupiter exploding would be the end of everything we know and could become. But Jupiter existing Jupiter, persisting Jupiter, continuing to guard the inner solar system. That's the foundation of everything we are. So, the next time you're outside on a clear night, take a moment to find Jupiter. It's not hard. It's one of the brightest objects in the sky. And when you see it, remember that you're not just looking at another planet. You're looking at your guardian, your protector, the reason you're alive to look at anything at all. And maybe whisper a quiet thank you to the darkness, because that bright dot of light 500 million miles away is the difference between a universe where humans gaze at the stars and wonder, and a universe where nothing gazes at anything because nothing complex enough to gaze ever survived. Thank you for joining me on this journey through cosmic catastrophe and cosmic gratitude. I hope it's changed the way you see the night sky. I hope it's given you a deeper appreciation for the delicate balance that makes our existence possible. And I hope it's reminded you that sometimes the most important things are the ones we never notice, until we imagine them gone. The universe is full of stories like this. Stories of invisible protections, unlikely coincidences, and the razor's edge between existence and oblivion. And I'll be here to explore them with you, one cosmic mystery at a time. Until our next journey together, keep looking up, keep wondering, keep asking questions. And every time you see Jupiter shining in the night sky, remember you're looking at the reason you're here to look at all. Clear skies, everyone.